Hi everyone, in this short video I'm going to talk to you about section 5D, standard cell potentials. And what I need you to do is to get out that tan paper that I copied for you that has standard reduction potentials at 25 degrees Celsius for a whole bunch of different species. And what you see on that page are a bunch of half reactions, and I want you to notice that all of the half reactions are written as reductions. Each of the species is gaining electrons to produce a reduced product. And all of those species are in order by their abilities to be reduced. So the F2 that you see at the very top of the table is very likely to be reduced. It makes it a very good oxidizing agent. And in contrast, if you look at lithium, which is at the bottom of the second list, very unlikely to be reduced as a species. It makes a terrible oxidizing agent, but makes a terrific reducing agent. So the question is, where did these numbers come from? Well, you see in the picture below a cell that's set up with copper on one side and hydrogen on the other. Chemists have made the decision that they're going to call the half reaction, half cell reduction potential for hydrogen 0. So if you find hydrogen on that tan sheet that I gave you, it's in the second column, it's about a quarter of the way down. Its half cell reduction potential, that E value, is just given a value of 0. It's kind of like deciding that the freezing temperature of water we're just going to call 0. That was the decision that was made. So that's our standard. So what happens is we take a species like copper and we put it in an electrochemical cell with hydrogen and we measure the voltage on a voltmeter and we determine how the electrons spontaneously flow. It's important to understand that the concentrations of the solutions that are in the two beakers have to be at 1 molar. The temperature of the system has to be at 25 degrees Celsius. And this has to take place at a standard atmospheric pressure of 1 atmosphere. It turns out in this particular picture that you're looking at right here that electrons will spontaneously flow from the hydrogen to the copper. So in this case, copper is more likely to be reduced than hydrogen is. And so it's given a positive half cell reduction potential, and the voltmeter will tell us what that half cell reduction potential is. It's that 0.340. Here's another electrochemical cell where we're looking at zinc in an electrochemical cell with hydrogen. And notice that in this case, the electrons are flowing towards the hydrogen instead of away from it. So in this case, the electrons will spontaneously move away from the zinc. So the zinc is not going to be reduced when it's put in a cell with hydrogen. The zinc is going to be oxidized. So because zinc here is much less likely to be reduced than hydrogen, it's given a negative half cell reduction potential. Now again, on the voltmeter, you're not going to see a negative value. That's misleading. But we give it a half reaction reduction potential compared to hydrogen as a negative, and the negative simply tells us that the zinc is less likely to be reduced than the hydrogen is. It's not going to be the oxidizing agent. It's going to be oxidized itself, and the hydrogen in this case is going to be reduced. So that's where those numbers come from. It makes sense then, if you look at this picture where we have zinc and copper in an electrochemical cell together, that because copper, again, was much more likely than hydrogen to be reduced, and zinc was much less likely than hydrogen to be reduced, that copper in this cell is going to be the cathode. It's where the reduction is going to take place. What I want to explain to you now is where we get this value right here, this 1.103, where we get this, the cell potential for the overall reaction for any given electrochemical cell at standard conditions. So to do that, I'm going to do a sample problem off of page 12 and just explain the process. So question number 1 reads like this. Calculate the standard cell potential produced by a galvanic cell consisting of a nickel electrode in contact with a solution of nickel plus 2 ions and a silver electrode in contact with a solution of silver plus 1 ions. Which is the anode and which is the cathode? To solve this problem, what you want to do is go to your standard reduction potentials sheet, that tan sheet, and I want you to write down 2 half reactions as reductions, one for the nickel and one for the silver. So this is what you're going to end up writing. Nickel plus 2 electrons will reduce to nickel metal, and it has a half cell reduction potential of negative 0.23. The silver, Ag plus, will gain an electron and reduce to silver metal, and it has a half cell reduction potential of positive 0.80. So what that means to you is that the silver is much more likely to be reduced than the nickel is. It's more likely to gain electrons. So silver is a much stronger oxidizing agent. So in this particular cell, silver is going to be the one that's going to be reduced. Therefore, silver is going to be your cathode. Because remember, the reduction takes place at the cathode. And nickel, on the other hand, is going to be your anode. Because the nickel, in comparison with the silver, is not likely to be reduced. It's much more likely to be oxidized. So what you're going to do is rewrite these 2 equations down below. But you're going to take the nickel and you're going to write it as an oxidation, because that's actually what's going to take place in the cell. Nickel will oxidize to nickel plus 2 electrons. And now I'm going to take its half cell reduction potential and I'm going to flip the sign, because now I've got an oxidation taking place, positive 0.23. And because the silver is going to be reduced, I will write that reaction as it appears above to produce silver. And that half cell reduction potential is going to stay just what it was before. I didn't flip the equation, so I don't flip the sign. And you simply add up the 2 potentials. And my answer is positive 1.03 volts. I want you to notice that the electrons did not match in the 2 equations. You do not have to balance electrons. Just ignore them. Don't multiply them. This is all you need to do to determine the voltage that you would see in a cell where you had nickel and silver as electrodes in 1 molar solutions of their respective ions at 25 degrees Celsius. So what I want you to do is see if you can do the problems on page 12 and 13. The answer key is given at the bottom of page 13. Try the next problem. If it works out for you, great, keep going. If you're not getting the right answer, just stop me in class and we'll talk about it. Good luck.
Made with Doodlecast Pro.